Welcome to AI Podcast. I'm Daniel, and today we're unpacking a paper from DeepSeek-AI about teaching large language models to reason using reinforcement learning. The quick takeaway is this. The team shows that a model can learn strong step-by-step reasoning largely through reinforcement learning with simple, checkable rewards. With a small warm-up of supervised examples and a staged training recipe, their system called DeepSeek-R1 reaches top-tier results on math and problem-solving benchmarks, and then distills that skill into smaller models that run cheaper.
That's a strong opener. So if I'm a busy listener, the headline is that reinforcement learning can, on its own, unlock reasoning in these models, and the final system stands up well against the strongest closed models. Did I get that right?
Exactly. Now a bit on who did the work. The paper is by Wenfeng Liang and colleagues at DeepSeek-AI, posted in January 2025. It's a very large team, but you can think of it as a DeepSeek-AI effort led by Liang.
Got it. Before we get into the nuts and bolts, what problem are they trying to solve? We've heard a lot about reasoning lately.
The backdrop is that today's language models are great at fluent text, but reliable reasoning, careful, multi-step thinking that holds up under scrutiny, has been inconsistent. Some of the strongest results have come from closed systems, like the O1 series from OpenAI, which popularized test time scaling, meaning you let the model think longer. In the open community, people tried supervised fine-tuning on chain-of-thought data, training neural reward models to score reasoning quality, and even search methods like beam search or Monte Carlo tree search. Those helped, but they didn't consistently match the best closed models across a broad set of tasks.
So there's a gap between flashy demos and everyday reliability. Where does this paper step in?
The authors ask whether you can get reasoning to emerge with reinforcement learning alone, avoiding heavy dependence on large supervised datasets or a delicate neural reward model that can be gamed. Their answer is yes, with the right incentives. They start with a capable base model, give it rewards for being correct and for clean formatting, and optimize it with a lightweight algorithm. That already gives you a big jump in reasoning quality. Then they add a small cold start with long step-by-step examples to stabilize things, run reinforcement learning again in stages, and later distill the skill into smaller models.
When you say lightweight algorithm, what are we talking about in plain language?
They use something called group relative policy optimization. In practice, for each question, the model generates several candidate answers. Instead of training a separate critic network to tell good from bad, the algorithm compares those candidates to each other. If one answer gets the reward, say it solves the math problem and follows the required format, it becomes the within-group reference, and the model nudges itself toward that behavior. It's cheaper and simpler than training a big critic.
I like that. No heavy extra machinery. Just compare the model to itself. And the rewards are simple too?
Yes. Two main pieces. One is correctness, which is easy to check in math or coding. Does the final answer match the ground truth, or does the program pass its tests? The second is format discipline. The model is told to put its private reasoning in a think section and the final, short answer in an answer section. If it keeps that separation clean, it gets rewarded. No learned reward model, just rules you can verify.
So they're nudging the model to think carefully, but also to be tidy about how it presents the final answer. What happens when they actually run this?
First, they try pure reinforcement learning without any supervised warm-up. They call that R10. Even that setup pushes performance up dramatically on math competition questions. The model learns to reason in steps, but its writing can be messy and it sometimes mixes languages. Then they introduce the full recipe, called DeepSeek-R1. They add a small cold start with long chain of thought examples, continue reinforcement learning in multiple stages, harvest high-quality traces from the trained model, do a brief supervised pass on those, and finish with another round of reinforcement learning across a wider set of tasks.
And the results?
The headline result is on a well-known math benchmark called AMY 2024. DeepSeek-R1 hits pass at 1 in the high 70s, essentially on par with the best closed models reported at the time. On another math set called Math 500, it's in the high 90s. The team also tests programming skill in a live setting and estimates a Codeforce's ELO a bit above 2000, which places the model around the mid-90s percentile among human competitors for that period. The overall story is that reinforcement learning focused on correctness and format can reliably sharpen STEM-style reasoning, and those gains generalize to long context analysis and other tough problems.
That's impressive, and it sounds practical. You mentioned distillation. Why is that important?
Training a giant model with long reasoning traces is expensive. Distillation lets you copy the reasoning behavior into smaller, cheaper models. In their experiments, a distilled model around 32 billion parameters scores in the low 70s on that same AIME benchmark, which is strong for its size. In short, you can deploy something lighter that still carries much of the teacher's reasoning skill.
So a company with limited compute could still benefit. I'm curious about the experimental setup. Were they only looking at math and code?
Math and code are central because correctness is easy to check, but they also evaluate knowledge and reading comprehension with benchmarks like MMLU and GPQA. On those, DeepSeek-R1 improves over the base model, though it doesn't always top the strongest closed systems. They also include open-ended preference evaluations where other language models act as judges, reporting length-controlled win rates on Alpaca Evil 2.0 and strong results on Arena Hard.
That's thoughtful. Now, every paper has trade-offs. What should listeners keep in mind before they treat this as a solved problem?
A few things. First, general product skills, like strict JSON formatting, tool use, or complicated multi-turn role-play, do not automatically improve just because reasoning improved. In fact, R1 can trail their earlier general-purpose model on those fronts. Second, the model can mix languages in its internal reasoning or occasionally in outputs, which is distracting outside English and Chinese. Third, the system is sensitive to prompting. Clear zero-shot instructions with an explicit format work well. Fourth, coding tasks remain challenging to scale for reinforcement learning because each evaluation cycle is slow, so the gains there are more modest. And finally, while the paper gives a solid training recipe, it doesn't fully detail the compute budget and all hyperparameters you'd need for perfect reproducibility at a new lab. That's common, but it matters if you want to replicate the result at scale.
Right, so it's a big step, not the finish line. I have a question about the choice to avoid a learned reward model. Doesn't that limit what you can reward?
It does limit the breadth of what you can measure, but that's also the point. Simple, verifiable rewards are harder for the model to game. If you train a neural reward model to grade good reasoning, the policy can learn to exploit quirks in the grader. By sticking to correctness and format, you keep the objective tight and trustworthy. The trade-off is that you focus on domains where you can check answers automatically, at least to bootstrap the behavior.
Makes sense. Could this extend to more open-ended tasks like helping a developer refactor a messy codebase?
That's one natural next step. You'd want better program analysis rewards, partial credit for intermediate progress, and faster feedback loops so reinforcement learning can scale. The paper sketches that direction but doesn't claim it yet. Another direction is bridging reasoning with tool use, giving the model calculators, retrieval, and function calling, and then rewarding not just the final answer, but how well it orchestrates tools. They also flag multilingual stability as an area to improve, so rewards and data curricula that prevent language mixing would help.
And on evaluation, I imagine we still need stronger guardrails against contamination and judge bias.
Exactly. They already time-bound some code benchmarks to avoid training on the test set by accident, which is good practice. More human audits, adversarial test suites, and contamination-resistant datasets would raise confidence further. And on transparency, sharing more about compute and ablations like how many samples per prompt, how long the traces are, and how rewards are weighted, would make it easier for others to validate the recipe.
Let me try a short recap for listeners. DeepSeek AI, led by Wenfeng, Liang, and team, shows that reinforcement learning with simple rewards can make a large language model reason better. Start with a capable base, reward correctness and clean presentation, compare multiple candidate answers per question to guide learning, and then stabilize with a small supervised warm-up and staged training. The resulting model performs at a very high level on math and does well on coding and knowledge tasks, and you can distill that skill into smaller models. Limitations include tool use, formatting strictness, language mixing, prompt sensitivity, and open questions about compute and reproducibility. Did I miss anything important?
That's a great summary. I'd add one nuance. The biggest gains are in STEM-style reasoning, where correctness is crisp. The improvements on general conversation and product-style tasks are uneven, so expect to combine this recipe with other training that targets tooling and structured outputs.
Understood. Final thought. If a CTO is listening and asking, should I care now or wait?
If you depend on math, analytics, or code generation where correctness checks are available, this matters now. The recipe is practical and uses rewards you can implement. If your product lives on function calling, multi-turn workflows, or strict schemas, consider this a promising foundation but plan additional training and evaluation. Either way, the big idea is that we can incentivize reasoning directly with reinforcement learning, not just hope it appears from more data.
That's a clear call to action. Thanks, Daniel.
And thank you, Maya. That's all for today's AI podcast. If you found this useful, share it with a colleague who cares about trustworthy reasoning in AI. Until next time, take care.